Okay, we are now recording. Let's get from the current slide. Okay, now before we get on to this, let me go over these few announcements. We have coming up tomorrow morning, I do, what they call a planning hearing, and it's meeting on the Birmingham campus at 10 o'clock, which is really awkward because I have a class that ends here at 9:50, so I would have to leave early, okay, here on my class. But then, as it turned out, one of my instructors didn't get me his stuff until over the weekend, and even then didn't give me his documentation, so even though I've got his numbers and everything worked up, I have to wait, I have to get his documentation. So I'm going to have to go to the Birmingham campus tomorrow morning first thing, so I won't be coming to Bessemer campus at all until close to noon. Then I've got a class that goes from noon until 3:30, class and lab. So if you're looking for me tomorrow morning, wait till tomorrow afternoon. Sometime after 3:30, should be back in my office. Like I said, probably I'll be right up until 10:30 leaving Birmingham. 11:30 leaving Birmingham and driving here just to catch my 12 o'clock class. So there's that. Now, preempting that a little bit was the fact that the weekend I had to spend just about the whole weekend, what time I had to spend on it, getting ready that big report, the thing that we're doing tomorrow. So therefore, I didn't get anything graded. I think I already had all of this class graded. It's probably not on PowerPoint yet, okay, because I just didn't have a chance at all this weekend to work on PowerPoint. So the bottom line of that is, if you were looking for your most recent things you've turned in and don't see them on PowerPoint, on Blackboard, hang on, I'll try to get them there, but the earliest will be tomorrow afternoon. The earliest, okay. If I don't get them done by tomorrow at 5:15, it's probably going to be Thursday, either Thursday morning 10 to 12 or Thursday afternoon 3:30 to 5:15. Okay, that being said, let's talk about how we're going to wrap things up. Okay, we're now in Chapter 9. We should finish Chapter 9 rather quickly, I hope anyway. This is a long chapter, but hopefully we'll finish it in the first hour or so. And here is... Yeah, I know, I just can't find you. Brown, all right. Okay. All right. So let's go through this as quickly as possible. Going to try to have a lab today. Now here's another downside of having to do this report. Last Thursday, I spent just about all my office hours, in fact, any that wasn't being interrupted with having to register students for one thing or another like that, I spent on that report and had no time to get your lab done up. I had a lab prepared for this chapter many years ago, and I cannot locate it. I must have loaned it to somebody for them to use and then never got it back. So the lab we do today, you'll be doing on paper, okay? Line paper, blank paper, whatever kind of paper, you'll have to write it out, and I'll describe to you how to do that, okay? So sorry I don't have this one worked up for you. Which also means I'm pretty sure I don't have the test prepared yet either. So tomorrow afternoon when I get back, that's one of the big things I'll be trying to get done, is getting your tests made out for this chapter. But like I said, this thing coming up this late in the term is awful. I mean, it's just almost the worst possible timing, but that's what they want to do. Okay, they don't ask us, they just tell us when they're going to have them. It doesn't matter about classes or end of the term or anything else. Okay, so today we should finish Chapter 9. We should be able to do the lab in Chapter 9. I don't think the lab will take you super long, so we will do the lab in Chapter 9. And then, and like I said, I don't have the test ready, so I have to get that to you on Wednesday, hopefully. Okay. Then, what do? We meet Wednesday, and Wednesday we will jump over. No, it's no jumping. We go straight into Chapter 10, which is thermal physics. Okay, so we will start Topic 10 on Wednesday, and should move along fairly well. I don't know if we'll have a chance to do the lab or not, but if we don't, the lab we can take care of the following Monday, because we do have class the following Monday. On that following Monday, I will give you your test for this chapter, this topic, 10, and that will be your last test. Okay? It'll count as a final exam. So let's talk about that a little bit. I'll give it to you Monday. I'll take it back anytime you finish with it. Okay, now if they had emailed me something about needing hers early, and she said something early in the term, don't remember, I was hoping to see her today and find out, but she's not here, so I'll just have to wait and see. But anyway, we will, I'll give it to you Monday, and you get it back to me anytime Tuesday. In fact, if you finish it Monday afternoon, you can turn it in then and be through, okay? Tuesday, anytime, I'll be here 7:45 in the morning until 5:15 in the evening. Wednesday, I'll be here 7:45 in the morning until 9:15 in the evening. And Thursday, I'll be here 7:45 in the morning until 5:15 in the evening. I need it. I need that, everything that you're going to turn in by Thursday noon. Okay. Now, let's talk about other things that are due. Sorry to take this much time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This class is next to my best class, my best big class about getting papers in. 10 out of 22, that's still less than half. Fewer than half of you have turned in your research papers. Yes? You got it? Fantastic. Now, exactly half of you have turned in your research papers. Okay? So please get those to me as soon as you can. If you can get them to me by Wednesday, that would be great. You'll still get 1 bonus point if it's in by Wednesday. You get 0 bonus points if you turn it in Monday, but you get your all score. If you turn it into me after Monday, then you start losing points. Okay? So please get that in to me sooner rather than later. All right? All tests and labs should be into me by basically pretty much the beginning of class next Monday. Because once I get them all in, I'm going to return everything back to you, everything that you've turned in so far. Okay? I've started returning some of those things. If you haven't received your test 1, then please see me either around lab or after class or sometime like that. What's that? I can't hear you.
I gotta get a couple of tests from you.
Okay, right. Okay. I've returned test 1, test 2, and I believe test 3. I haven't returned test 4 because I'm still missing one of those. Okay. Labs, I haven't returned any because I'm missing at least one in every one of the labs. I don't know if that person is going to turn them in or not. Hopefully she'll turn in something and I can get those back. Okay? So please get me everything by Monday. I'd rather have everything Wednesday, tomorrow, the day after tomorrow if I can, but than anything else. Like when I give you your test for this chapter on Wednesday, of course you get that back to me by Monday. Okay. All right. And then get me your final by noon. Try to get that to me by noon on Thursday, because even though we're going back to a 5-day work week, that first week in August, I won't be here that Friday because I've got an infusion that day, so I will not be on campus at all. The infusion starts sometime like 8 in the morning. I have to be in there for labs, and it usually goes all day long. So I won't have any opportunity to be on campus that day. So I'll need them because I haven't heard for sure, but I believe grades are due by noon on that Friday. Okay, so I've got to have everything graded Thursday before I leave. All right. Any questions on anything we've done so far? What the procedure is for the rest of the term? All right. We're beginning in the text. It's 9.8.1. This is on page 295 in the on the slide set. This is section 9.9, but in the text it's 9.8.1. And I think we talked about surface tension last time, and so we're now going to do a closer look at the surface of liquids. In your text, it's just called the surface of liquids. There's two forces going on here. One is cohesive forces. Those are the forces between like molecules, okay? And water has, I've said several times, one of the strongest cohesive forces between the water molecules of just about any molecules out there, to be a liquid. Those are really strong. But you also have adhesive forces. And generally, water molecules are fairly adhesive as well. These are the forces between unlike molecules, okay? Say water to glass, water to, a surface like wood or metal or something like that. Or alcohol to, glass or something like that. Any forces that are tightly different molecules wanting to really connect together. The shape of the surface depends on the relative size of the cohesive and the adhesive forces. Now, I said that water has pretty strong cohesive forces, but it also has very, very strong adhesive forces. So, in water, this adhesive force in many of these is greater than the cohesive force, even though that cohesive force is quite strong. For instance, water to glass, water will actually climb up the side of a glass. You've probably seen that. I don't know, that's probably a plastic, not a glass. Can I look at this just for a moment? Okay. If you look carefully, you can see that there's a little bit of a lip where that water does go up the side, just a little bit. Okay? Now, the liquid clings to the wall of the container, and the liquid wets the surface, and then, and it's not all that this is a little overstatement. The adhesive forces are greater than cohesive forces, but it's a little more than that. The water is strongly attracted to the glass, but then it pulls other water molecules with it because of the cohesive forces. So it's a combination of adhesion and cohesion here that water pulls it up. Now, what we call this surface of water, especially if this was a small tube, like a capillary, we call that the meniscus, this curved surface of the liquid. And this is a concave up meniscus. It shows us going for a long way here. If this were a small tube, then it would actually have a minimum and then go right on up and climb up the side over here, just like that side. Okay, so the liquid wets the surface and crawls up that surface. Water is notorious for doing this. Okay? On the other hand, mercury doesn't like glass, and it doesn't like much of anything else. It's very, very strong cohesive forces, okay? Here the cohesive forces are greater than the adhesive forces. The liquid curves downward, and the liquid does not wet the surface at all. Now they show these angles in here, and both of them are called phi, and that's the angle that it makes with the glass to the tip of the meniscus, okay? And again, the angle between the glass and the tip of the meniscus here. That one's an obtuse angle, meaning it's greater than 90 degrees. The other was always acute, less than 90 degrees. Okay? Now, part of the reason for this, I'm pretty sure, hey, mercury doesn't seem like it should even be a liquid. It should be a solid. You look at everything else on the periodic table, anywhere close to mercury, and it's a solid, okay? Mercury is a really, really unusual liquid in that it's such a high density. Here mercury is, down here, atomic number 80. 80 protons in that nucleus. Atomic mass, almost 201. So that means there are 121 neutrons in that nucleus. This is one big, heavy molecule or atom to be a liquid. So therefore, since it's such a big one, these things really stick together. They're almost wanting to become a solid, okay? That's how tightly they stick together. And mercury, like we've already said, gold is less dense than mercury. Platinum is less dense than mercury. Rhodium, I can't think of the name of that one. Osmium, I don't know, osmium may not be, but many of these things are. Lead is actually less dense than mercury, but it's higher on the periodic table. But if you go up you have to go up several rows before you find liquids or gases. It's just incredible how heavy mercury is to still be a liquid. I think that's part of the reasons those molecules really stick together, hang together quite well. The cohesive force is much stronger. And then, so therefore with mercury, if you had this in a capillary tube, your meniscus would be concave down, or convex up, or however you want to say that. It would be that way. So, and generally when we're reading surfaces of liquid, we go to the center of the meniscus. That's what we'll read. If this was a graduated thermometer or a cylinder or anything else like this, we wouldn't read down here, we'd read here. And similarly, we wouldn't read up the side, we would try to read the lowest part, the minimum there of the meniscus. Okay. Now, this is the contact angle. I was hesitant to say the type of angle, but it's a contact angle. The angle phi between the solid surface and the line drawn to the tangent of the liquid at the surface is called the contact angle. So you just continue what this line here, the tangent line at the surface, continue that up. So that would be the contact angle there. Here's a tangent angle downward here, and the angle between that is an obtuse angle, phi also, between the solid surface and the line drawn tangent to the liquid. That's called the contact angle. In A, this angle, the contact angle is, I got this backwards. Sorry about this. Let me make sure that they haven't labeled something wrong. Yeah, they've labeled it backwards here. This should be a less than sign. Phi is less than 90. Go on and change that on the slide. Can't believe this. This is less than 9. Oops, let me get my... Okay. this is less than 90, this is greater than 90. Okay. In A, phi is less than 90, and the cohesive forces, no. Let me change that. All right. Here's the easiest way to make this change. In B, my pen's not coming up. There we go. In B, theta is greater than 90 and the cohesive forces are greater than the adhesive forces. In A, phi is less than 90 and the adhesive forces are greater than the cohesive. So they had this part right, this part wrong. Okay. So that was easier to change one thing than two. Okay. In B, the angle is greater than 90. It's an obtuse angle. The cohesive forces are greater than the adhesive forces. And in A, theta is less than 90 and the adhesive forces are greater than cohesive. But like I was saying with water, okay, it is a combination because it is stronger adhesive, but then the water molecules pull the other water molecules up, which means the adhesive are still cohesive are still pretty great. Okay. And this leads to what we call capillary action. Okay? Now, the book, your new edition of the book has another picture here, figure that the slideshow doesn't. Figure 943 at the bottom. And you'll have to just look at that in your own book. But they show water on paraffin. Now, paraffin is what kind of material? Anyone know what paraffin is? Y'all wouldn't know this either, but way back when I was growing up, my mom put up a lot of jellies. You know, we picked plums and blackberries and things, and she'd make jelly. I mean, lots of really good jelly. And she didn't always have lids that would seal well, so what she did, she put paraffin wax, basically melted wax, put it on top, and it made the seal. Okay, that was my first introduction to paraffin that I recall, but basically is a wax. How does water and wax interrelate? Well or badly?
Water and wax.
Right.
Wax kind of repels water.
Absolutely. Okay. So water and wax are called. Wax is called hydrophobic. In other words, it's scared of water. You know, it doesn't get close, and water would be waxophobic. You know, it doesn't want to get close to it, and therefore it will beat up. That's why you wax your car, right? And the water beats up on it and doesn't penetrate or you know, damage the appearance of the car. Whereas water on, say, another wetted surface, the water will then spread out. And you can, again, think of your contact angles in those kind of terms. Okay, this is Monique. On the wrong page. Monique. All right. All right. For those who have come in late, I'll not go through everything again, but please remember your research papers are due by, well, as soon as you can get them in to me. But you'll still get a bonus point if you get it in today, tomorrow, or Wednesday or Thursday. If you get it to me Monday, no more bonus points. If you get it to me after Monday, you start losing points. Okay? So please get it in sooner rather than later. Okay? Also, any tests and labs that you haven't turned in, try to get those into me if you can by Wednesday. The latest I can accept them is Monday. Monday is the last day of class. And on Monday, I will give you your last test, which will be a take-home. That will be the final exam, but it will be not comprehensive, just a take-home. All right. Capillary action. Okay? Capillary action is a result of surface tension and those adhesive forces. Okay? And what it is, a liquid rises in the tube when the adhesive forces are greater than the cohesive forces, just like we saw in the last slide. But with a capillary tube is by definition very, very small. Okay? So therefore, when the water goes up, or the liquid goes up a little bit, it really pulls it up. I mean pulls it up big time. So this isn't anywhere close to the surface of the water. This is way up here because that capillary action pulls it way up. The liquid rises in the tube when the adhesive forces are greater than the cohesive. At the point of contact between the liquid and the solid, the upward forces are shown in the diagram. So the forces are pulling up like that, so they're raising the water up the capillary tube. Now, I think you probably noticed this before. Do any of you know of someone who has to take, say, glucose samples of their blood or anything? Have you ever witnessed someone do that? They have those little capillary tubes. They prick their finger, get a little drop of blood, and take that capillary tube, and that blood goes just right up the tube because the surface tension and the adhesive forces here are sucking that blood right up into the glass tube. So, at the point of contact between them, the upward forces are shown and pulling, say, that blood right up that capillary tube. Okay? This, by the way, is 9.8.2 in your text. On the other hand, if you have cohesive forces stronger than adhesive forces, as in mercury down here and glass there, or this would also work if you had a waxy kind of capillary with water. When you have water is repelled by the waxy surface, and that would actually push the water down the tube. Here the cohesive forces are greater than adhesive. The level of the fluid and tube will be below the surface of surrounding fluid. Okay? The forces are down that way. And this height here would be related to the strength of those forces. Okay? Similar, the height here would be related to the strength of the forces of the capillary action. Okay. Scarlet? Yeah. Bottom part of the alphabet is looking pretty good. The top part's a little sketchy here. Okay. Good deal. Thank you. I'm sorry? What about them? Oh, okay. Okay. All right. I think we beat that one to death, haven't we? Okay. The height to which the fluid is drawn into the tube or depressed in the tube. Okay? That height, that H that I pointed out there, is going to be 2 times gamma. Does anyone remember what gamma is? What it was last week? I know it was a long time ago. If you turn back to page 293, you'll see gamma is the surface tension, and it's the force per unit length. Okay, the surface tension force per unit length of which, along which the force acts. So this height is twice the surface tension divided by the density rho, that's not a p, that's rho, g, the acceleration due to gravity, r, the radius of that capillary tube, and the cosine of the contact angle, phi. Okay? Now, remember I said the contact angle phi was an acute angle in adhesive being stronger when it pulls it up the thing. Well, there, the cosine of an acute angle is positive, so this will be a positive h. You don't have to put a sign in here, because once you do, when the cohesive forces are greater than the adhesive forces, like mercury, in a tube, then that phi is an obtuse angle, greater than 90. And cosine of a obtuse angle is negative. So there's where the negative sign comes. You don't have to do anything with it. It shows up there by itself. So h will be that, but h could be positive for an acute angle phi, negative for an obtuse angle phi. So there's a formula you might run into a little bit. Now, let's move on. There is on page 297, rising water. And by the way, let me just also mention this. What capillary are you most intimately involved with? Or are they involved with you? In your vascular system. Okay, you can see veins, you can feel arteries, okay? The blood pumping through the arteries, but everywhere you see any color in your skin, that means there are very fine capillaries that are there. That's where the action is, folks, in the capillaries, because the walls are very thin, and that's where gases, nutrients, and waste product and stuff goes back and forth into the blood through those capillaries. Okay? Very, very thin walls and very close contact, and they do all their exchanges there. The nutrients go to the muscle, the waste product comes back into the blood system, then your blood is piped on through your kidneys, your liver, and your other filtering organs in your body. And so we depend on those capillaries. That's why you prick your finger, you just cut a bunch of capillaries. They grow back, they heal and stuff, but that's what's happening. Usually, hopefully, you don't hit a big vein or something like that. Then you may have a gusher, but just a little prick and things like this is going to be in a capillary. So now let's talk about viscous fluid flow. What does viscous mean to you? Do you have any concept or framework in which to put the term viscous? Ever heard it? How about if I said viscosity? Ever hear that? Say again. Do any of you change your oil in your cars?
Yep.
All right. And what's on the top of most of those oil cans are on the side of the bottles? 10W30, 10W40, 30 weight, whatever. That's dealing with the viscosity of the oil. It's a very important property of oil, is to be fairly viscous. Okay? Why do they have the different numbers? When would you use one versus another? Especially seasonal. In the summer, you typically would use a little bit heavier oil, higher viscosity, because your temperatures are going to be a great deal more. Here in the southeast, it really doesn't matter. But if you go up in the Minnesota and northeast and North Dakota and those kind of areas, I bet you just about everybody up there is putting in a lighter weight, they call it oil, for the wintertime, because it's so cold, it gets so viscous, the oil hardly moves, and then it's not doing its job. In fact, it may actually be hindering the job it's supposed to be doing. So viscosity refers to friction between layers. between the same layers of a fluid. Layers in a viscous fluid have different velocities. We know that. We talked about this before. If you have a, did we mention PHY201 flow earlier? I'm teaching 6 different classes, and I talked about it in one of my classes. I thought it was this, maybe not yet. We'll get to it. But if you have water moving through a pipe, any kind of a thing here, the largest velocity is going to be near the center where you have the least friction. You have more friction near the surface, and the surface, that's going to slow down. In fact, right on the surface, technically the velocity is usually very close to 0. So, the more viscous your fluid is, the more easily it can move through that center of the pipe. But layers in the fluid, and these are usually layers that take the shape of your pipe or your ducting or whatever. This would be a circular layers, that would be a rectangular layer. You know, near the edges, your velocity is very slow, and the center would be great. The velocity is greatest at the center. Cohesive forces between the fluid and the walls slow down the fluid on the outside. Now, according to their definition, to me, there should be adhesive forces between the fluid and the wall, because those are dissimilar materials. I don't know why they say cohesive here. That should be adhesive forces between the fluid and the walls slow down the fluid near the outside. In fact, often, technically bring it almost to a stop. Okay? So, the coefficient of viscosity will assume that a fluid between 2 solid surfaces, okay? Upper surface, lower surface, okay? Fluid is required to move force is required to move the upper surface. So you're going to be pulling on this surface here. You're going to be pulling. A fluid is in between there, you pull on that, okay, on the upper surface, okay? That force that you'll have to do is, now this is the Greek symbol nu, okay? Lowercase nu. Nu is how it's done. Times the area between those surfaces, the velocity of the fluid, and that could be an average or any place, and the distance, the distance between those plates, okay, or surfaces. Nu is the coefficient of viscosity, coefficient of viscosity. The SI units for that nu are newtons that you get from here per meter squared. Well, this is meters, that's meters per second, that's meters squared. So one of these meters cancels that out, and you get meters squared per second. I'm sorry. This unit is meters squared per second, so nu must be seconds per meter squared, because those units have to cancel out and leave you only newtons here. So they Newton second per meter squared. Now that almost sounds like, to me, a Newton second would be a momentum quantity divided by an area quantity. So momentum per unit area. The CGS units for this are the PHY. Okay? That's CGS, that's not SI. So 1 PHY is equal to 0.1 Newton second per meter squared. Okay, now what has happened here? You're pulling this upper plate with a certain velocity, and this F used to be over B, and E used to be over A on top of B here. And what you've done, you've pulled that with a force, giving the upper plate of surface of velocity, and the distance you displaced it is delta x is v times delta t, the time interval over which you exerted that force. That would be the amount of displacement you get there. Okay? I think that's all you need from that slide. Okay. Here's Poiseuille's law. Who in the world was PHY201? Probably haven't run into too many of them. He was a physician, a doctor, medical doctor. May have even been, seems like he may have had a specialty, but I can't remember what it might have been. But anyway, he gave the rate of flow of a fluid in a tube with pressure differences. And of course you have pressure differences. In your body, your heart is providing that pressure difference. The pumping of your heart, the squeezing of the heart muscle, that is creating that pressure difference. So the rate of flow is delta F V per delta T. That makes it a rate that you're dividing by P. And that capital V is a volumetric flow, not velocity. Velocity is lowercase. So this is change of volume per change of time. How much volume of blood is moving down that artery or whatever. And it's pi r to the fourth. R is the radius of that tube, whatever kind of tube it is, a capillary tube in your body, a vein, artery, whatever it is in your body, times P1 minus P2. Okay, obviously for the blood or the fluid to be flowing in that direction, P1 must be greater than P2. So this is a positive quantity, okay? The time rate of change of that velocity flow would then depend on the radius of the pipe, the capillary, the vein, the artery, whatever it happens to be, times the difference in pressure, that's the driving force, divided by 8 nu, that's your coefficient of viscosity, times L, which is the length of that artery, vein, tube, pipe, whatever you're dealing with. Okay? All right, so that's PHY201's law. Rate of change of volume per unit time. Cubic feet per minute, cubic inches per second, you know, whatever your rate of flow is. All right. They did have another picture in the text. I think it's a pretty good one. I don't see them in the slide set. And that is, this is the B picture, 49.6B. They give a picture of 99.46. This is the B part in our text. The A part shows all of these arrows to be exactly the same length. What does that mean? That means there's no friction in that pipe and among the fluid in the pipe. There's nothing holding it back. It just all flows at a constant rate of speed, not at different speeds. All right, Darius is here. Okay. Again, this is the flow rate in cubic feet per minute, cubic meters per hour or minute or something like that. Cubic inches per second, you know, or minute. You know, it just could be any kind of a flow rate. The fluid's velocity is greatest in the middle of the pipe, always the case, and it is really tending towards zero on the edges. It usually is more than zero. All right. This is now beginning 9.8.5. We're talking about the Reynolds number. At sufficiently high velocities, a fluid can change from streamline, or what they call laminar flow, to turbulent flow. In other words, if the fluid is going along too fast, there is so much drag on the edges, on the boundary of that pipe or tube or artery or whatever it is, and the fluid is moving so rapidly that it actually, the edges hold it back, and it actually forms these little eddy currents. Okay, some of it starts going in the opposite direction. The onset of turbulence can be found by a factor called the Reynolds number, or Rn, or Reynolds number. Okay? Now you can look up and write your paper on who in the world is Reynolds, or how did he develop this number, or who uses this, or what fields of study we use this. The Reynolds number is rho, that's the density of the fluid, times v, the velocity of the fluid, times the distance between the walls of that structure, whatever you're dealing with, divided by n, which is the coefficient of velocity. So this Rn is 2,000 or below, that flow is streamlined. Okay? You don't have any eddies. If between 2,000 and 3,000 Rn, the flow is unstable. Okay? And if it's 3,000 or above, then the flow is turbulent, actually turbulent. So this unstable is in between streamline and turbulent. It may be going on sometimes streamline and then suddenly start being turbulent, or be turbulent for a while and then change back to streamline or close to streamline. It's just unstable. But at Rn 3,000 or above, it's turbulent and strictly turbulent. Okay. Example 915 is a blood transfusion, and 916 is turbulent flow of blood. Okay? You usually don't want that to happen. Okay? Now, 9.9 in your text, 9.10 in the slides here, is moving on to a new topic, and that is transport phenomena. Whenever you have movement of a fluid due to differences in concentration, okay, that's as opposed to difference movement due to a difference in pressure. Let me say this. Anytime you have movement of anything, but including fluids, you've got to have a driving force. Okay? Often this is a change of potential. It could be concentration change. It could be a pressure change. It could be a temperature change. Something is driving those things to move. Okay? So what transport phenomena, we're talking about movement of fluid maybe due to differences in concentration, and whatever is causing that difference in concentration, that's part of the driving force. Okay? Now, this is as opposed to movement due to a pressure difference. Sure, if you put pressure on something, you're going to make it move. But this is due to differences in concentration. Now, the really dumb example I give of this one, any of you ever done any gardening or helped in flower beds, those kinds of things? Yeah, okay? Now, if you've been at it very long, you know that Bermuda grass moves from areas of high concentration to low concentration. Because as soon as I was doing some weeding over the weekend, and there I was planting some, we had some things, my wife had cut some shoots off of a plant that we had bought because it was sort of going wild, stuck them in water, they rooted, so we were finding new places to put them. So I was putting them in our old herb bed, and sure enough, here came a strand of Bermuda grass. I pulled that. It went back several feet. It seemed like it was heading from the high concentration to low concentration, making its way to find that. Lots of things do that. That's often called osmotic potential, moving from high concentration to low concentration. When your blood has high carbon dioxide concentration, it moves by osmosis. Let me put it the other way. When your muscle tissue has high carbon dioxide concentration from being active, then it moves from there into the bloodstream by osmosis. It always is trying to go down the gradient. So this is movement not due to a pressure difference, but due to a difference in concentration. The concentration is the number of molecules per unit volume. Very similar to what we saw here. Well, not here. Where was it? Well, I can't see it now. But basically, yeah, this is it. Volume. This is volume per time. What we're talking about here is molecules per unit volume. So it's related. It's not quite the same thing. The fluid will flow from an area of high concentration to an area of low concentration. Salts do this. Lots of things do this. This process is called diffusion and also osmosis. Usually osmosis is more, say, gases, and diffusion is more salts or things like that dissolved in a liquid, but it can be other things like that. But it's always a concentration moving from high concentration to low concentration, and the concentration is number of molecules per unit volume. So let's look at diffusion in Fick's law. Boy, we keep running into these characters. Okay? This is on the bottom of page 300 in your text. Diffusion is molecules move from a region of high concentration to a region of low concentration. That's what diffusion is. The basic equation for diffusion is given by Fick's law, and that's the diffusion rate. And this rate is a mass rate. The mass per unit time is equal to capital D, which is your diffusion coefficient, times A, which is the area. This is your concentration gradient, your difference in concentration, C2 minus C1. Higher concentration at C2, lower at C1, that's what drives the motion. Divided by the L, that's the length over which that motion occurs, that gives you your diffusion rate. Now, diffusion coefficient probably has some units associated with it. Otherwise, I would try to relate these. But remember, concentrations are number of molecules per unit volume. Okay? And so you have all sorts of things mixed up in that D to get your conversions right, that coefficient, diffusion coefficient. Okay? Now, here's an example. Obviously, the concentration of molecules in this side of the box is considerably larger than that side. Concentration on the left is higher than the concentration on the right. And there is an imaginary barrier. If it's got that kind of concentration difference, it's probably a real barrier. Many of the molecules on the left can pass to the right, but very few will pass from right to left. Why? They go by the concentration gradient, always going from high concentration to low concentration. Why would they go back this way? There's nothing to drive them that way. A few may randomly go that way, but the vast majority of the movement is in the opposite direction. There's a net movement from the higher concentration to the lower concentration. Okay. Where it always goes. Now, osmosis, how does that differ? Diffusion is molecules move from a region of high concentration to a region of lower concentration. Osmosis is the movement of water from a region where its concentration is high across a selectively permeable membrane. Back when I was younger, they called that a semi-permeable membrane. Now they're calling it selectively permeable membrane. We'll go into that a little bit later. Enter a region where the concentration is lower. The selectively permeable membrane is one that allows the passage of some molecules but not others. Your cell walls are excellent at this, okay? Your cell walls want to keep in the protoplasm and all the things that they need to operate, but they want nutrients to pass back and forth pretty easily, and they want waste product, carbon dioxide, water, those kind of things to pass out fairly easily, okay? So that's what when I was growing up, it's called semi-permeable membrane. Now they're a little more specific about it, selectively permeable membrane. Okay. Now, let's look at motion through a viscous medium. When an object falls through a fluid, a viscous drag acts on it. Okay, I'm sure you've seen this before. You drop, say, a rock through the air, which, by the way, is a fluid. Okay, it's a gas, and it has viscosity. Very, very low, but what's pretty obvious evidence that air has viscosity? Friction. Anyone ever seen a meteor shower? Okay, what's causing that?
Like burning up in the atmosphere?
Absolutely. The friction is so great that material, which is usually a rocky material, actually glows. It gets so hot it glows. Yes, our air has viscosity. I think I've used the illustration before, riding down the road in your car. When I was young, we didn't have air conditioning, so we had the windows open. I loved to stick my arm out of the car and feel it just pull me back, you know. Especially when you did like this, you could, you know, streamline it and do things like that. It's just dumb. But anyway, yes, even air has viscosity. But water has greater viscosity. So when an object is dropped from the air into water, suddenly it slows down. Okay? You'll see a viscous drag acting on it. The force of resistance depends on the shape and velocity of the falling object. That's why the meteors burn up, because their velocity is enormously high, okay? They're moving at a rapid rate of speed way up in the atmosphere where the air is fairly thin even, but they're going so fast that the kinetic energy is enough to make them blow up. The resistive force on a small spherical object of radius r falling through a viscous fluid is given by Stokes' law. There's another name. If you have a dearth of topics that you could write on, here's another one. Who in the world was Stokes? How did he come up with this law, and who uses it? You know, what fields of study does your field use? This is the resistive force. That's the force due to the resistance, and it's equal to 6 pi. There's a good old nu. What is nu? The coefficient of viscosity. That's what we do with this fluid. R is a radius, and V is velocity. Little v is velocity, capital V is volume. Okay. How do we remember those? Okay. Stokes' law. Now, since we do have Stokes' law, that this is a resistive force, now let's think. It goes back to Aristotle in many ways. The force due to gravity is pulling something toward the center of the earth, right? Okay? Always toward the center of the earth. And because that is accelerating to the center, it's picking up speed. Embry, right? Okay. I'll find it there. I got you right off the top. Okay. Picking up speed. Well, the resistive force, this is a constant, that's a constant, that's a constant, depending on the fluid, the coefficient of viscosity, or, depends on, if you're going through a large or small opening. But here's velocity. The greater the velocity, the greater the resistive force. So wait a minute. Here we have a force, gravity pulling down, constantly accelerating, meaning increasing the velocity, but the resistive force is increasing with that velocity. At some point, these two equal each other. And if they do, then they have what you call the terminal velocity. And that's what this slide is about, terminal velocity. As the object falls, three forces act on the object. Okay? First, the weight is always pulling it down. Always pulling it down. As the speed increases, so does the resistive force. Okay, now this is showing in a beaker, so it would have the weight pulling here and resistive force here. But with a fluid, you have also the buoyant force, Archimedes buoyant force pushing upward. So that is the third force acting on it. Now, all objects in air have a little bit of buoyant force because of the air. Usually that's so minimal that we ignore it. But I think when they were doing careful studies here, they realized, especially in fluids, when it's immersed in something, you have to include the buoyant force, or else you really your numbers won't come out right. And remember, the buoyant force is the weight of the displaced fluid here. So the bigger this thing is, the greater the buoyant force, and the denser this fluid is, the greater the buoyant force. So those things enter into that picture. And for fluids that have large buoyant forces as opposed to air, then that will increasingly become a fact. At a particular speed, called the terminal speed, then that force is zero. So in other words, then what you have to do, instead of the resistive force, and I don't know if they don't really do a good job of, they do a fair job of showing this. If you go back to that formula there, the resistive force, 6 pi nu RV, okay? And the greater the velocity, the greater that resistive force, okay? And when that's equal to mg, which is your weight, and minus the buoyant force, okay? And that's the weight of the displaced fluid, okay? Then that T here, divided both sides by 9 nu, and solve this for V, and that becomes the terminal velocity, when one force equals or balances the other. Okay? Now, I don't see that they have the buoyant force in here, and I'm guessing they don't, but I can't remember for sure the derivation if that was included here. I tend to think not, but it may have been. Okay. All right. Now, continuing with terminal velocity, Stokes' law will not work if the object is not spherical. Stokes' law is based on spherical geometry. Now, sometimes it may be a good approximation to it because it's basically all we got. So let's say a rock coming in from outer space, it may not be spherical, but if it's close enough to spherical, then you can probably follow it that way. I take it, let's see. I won't give that exactly. Assume that the resistive force has a magnitude given by F sub k is equal to kV. Okay? In other words, all these other constants we've lumped all together to make it k. So if you go back to this 6 pi nu rho r, all those multiplied together, we're going to name a new variable k. Okay? Just because 6 pi, they're just numbers. The nu, if you're all in one medium, the viscosity is the same, and the radius, whatever object you're moving through. Okay? All right. Assume that the resistive force then is all those others are lumped into one constant k, constant velocity. K is called the coefficient to be determined experimentally. Okay. Then the terminal velocity becomes something like this. Okay, mg, that terminal velocity. Now let's go back to that formula. This one. Okay. When you substitute some of the other things in the k rather than the, get those all grouped together appropriately, then this becomes your terminal velocity. mg, that's your force, your weight of the object falling, divided by k, that's your coefficient to be determined experimentally. That relates the resistive force to the velocity. Okay? And this is multiplied by 1 minus rho f divided by rho. Now, what in the world are we talking about there? Rho f would be the fluid density, and rho would be the density of the material that happens to be falling. Okay, so you see this ratio here basically is tied up with it comes from the buoyant thing. Not just that, but that's part of it. Okay, and the closer that the fluid is to the air or the other mediums you're dealing with, then this will be minimized, and it'll be approaching 1, and 1 minus 1 is going to be a pretty small number, so the terminal velocity will be quite slow there. No, yeah. Now, as I've been referring to terminal velocity, I've been thinking of things falling through the air, or through water, or through some fluid medium. Okay? Now, falling through those, okay, it seems like those forces are particularly adept at retarding the motion, but in reality, they just are there. Okay, they're not doing anything special to do. It's just because of the viscosity of the fluid. Okay, now the speed at which materials fall through a fluid is called the sedimentation rate. Now, this is not stuff you're dropping from above, but materials that are there. In my physical science class, we were talking a lot about erosion, and we've had some pretty heavy rainfalls this spring and summer, right? And here's FA. Okay. And when those things fall, big heavy drops of rain, if you have exposed soil there in your yard or wherever it is, then those big heavy drops of rain at a high rate of speed, they have a lot of kinetic energy, they fall and hit that soil surface and disperse the soil surface. That's called detachment. And the rate of detachment is related to the speed of that raindrop. And the mass of the raindrop is kinetic energy. So once that is detached, then also gravity sets in and pulls the water downhill. And when it does, there goes your soil. There goes particles. Okay? Now, if that, so you have things suspended in the water. Okay, and as long as the water is moving fairly rapidly, it hauls them with it. But if that water slows down a little bit, like it comes off of a hillside and slows down in a flat level area, then the things that were suspended start coming out. And that's called your sedimentation rate. The speed at which materials fall through a fluid is called the sedimentation rate. It is important in clinical analysis. Whose clinic? I don't know. That's sort of a strange line to be in there. This rate can be increased by increasing the effective value of G. How do you do that? Because then you are creating what they call a centrifuge. You're creating more centripetal acceleration. Not just the acceleration due to gravity, but a greater one. And I'm trying to think of some practical examples here. Well, here's one. What is the last cycle in your washing machine before you take out your clothes? It's the spin cycle. And why is it?
It gets the water out of your clothes.
Exactly, because it's now spinning at a great rate of speed, which increases the acceleration outward. So the water and the clothes are held in, but notice your tank, the drum inside your washer has these holes in it. Water can get out, your clothes hopefully stay in, and sure enough, the water is removed from there. Okay? So that would be, that's in some sense a centrifuge. Now, Ryan, I don't know, when I didn't see you come in, I was about to miss you. Okay, so Ryan's here. Okay, has anyone else come in? I didn't call your name when you came in. I guess Ryan's the only one that's tried to sneak by. Okay. So that's why increasing the effective value of G by creating centripetal force. Okay? Spinning things. Now, what are some things we centrifuge? Say again? Mud? Yeah, okay. Oh, blood. Yeah, okay, I got it. Anything you're trying to separate. When I was young, very young, we had a milk cow. My mom milked her twice a day, every day, no matter what. And she would skim off the cream, let it sit, skim off the cream, and then we would churn the butter. And the act of churning the butter is basically centrifuging, and the heavier solid butter materials would stick to the side, and the liquid would be in the middle. That would sometimes be called whey, or perhaps that's where the buttermilk, or I think the buttermilk was after you skimmed off the butter. But anyway, you would separate things that way. Y'all have already been here, haven't you? Yeah, you were in here earlier, weren't you? Okay, I marked you. Somebody came in and I marked. Sorry. Well, I got you now. Okay. Let me count and see how many people. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 2, 4. It was Ryan that came in. So I did see you when you came in, but you must have brought something up here, right? You didn't. Well, for some reason, I marked you as hilarious, but I got you both now. So let me go get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 2, 4, 6, 8, 10, 12, 14, 15. So I got everybody. Okay, that's centrifuge. So I bet you in dairies, when they're making whole milk, well, they just take the whole milk. But when they're doing 2%, they spin out enough to get part of the butter out and leave only 2% butter fat. Spin it some more and get more out and I only have 1% butter fat. Spin it a little more and get 0.5%. And if they spin it until they get all the butter they can, what's left is skim milk. Okay? I try to drink that because I got plenty of my own fat. I don't need the butter fat. All right, so that's what a centrifuge is. You have it in science. You have it in, like Ryan said, in blood. When you're separating out the components of blood, you use a centrifuge. High angular speeds give the particles a large radial acceleration, much greater than g, and in the equation g is replaced by omega squared r. I said in the equation, this equation here, instead of mg, m omega squared r. Okay? Now, anyone know what omega is? By the way, it's a Greek letter, lowercase Greek letter. Actually, the last letter in the Greek alphabet. And that is your angular speed. Angular speed. That would be radians per second. So basically, there's such thing as a radian, so it's per second squared. R times per second squared would be radian per second. I mean, meters per second squared. That's basic g, your acceleration. Now, I don't know if you followed the political situation back a few years ago when they were putting all these sanctions on Iran. Remember what they were about? We still have them in place, by the way.
Nuclear.
Yes. And what was one of the things they gauged by whether Iran was complying well or not? They tracked the centrifuges going in, because uranium is a very rare element. And what they do, I don't know what the whole process is, but once they've got it, say, in a solution, they centrifuge it to make it pure. And when Iran was caught purchasing these really high speed, high efficiency centrifuges, there was no imaginable use for that except separating out what they call the yellow cake, which is the really high uranium content. And when they say weapons grade, they mean it's really been refined to the most concentrated form. Centrifuges do that. Okay. The particle's terminal velocity will then become, and this is that formula I was showing you before, the terminal speed was what was mg over k times 1 minus rho f over rho. Now it's m omega squared r, which again, this is per second squared times meters. So the meters per second squared, that's an acceleration, but it's based on an angular speed. The particles with the greatest mass will have the greatest terminal velocity. Okay? They'll be have to go faster before they reach that terminal speed. Okay? The most massive particles will settle out at the bottom of the test tube first. Okay? Now, when I was in the Navy, I went through Navy ROTC at college, and I was lucky enough to be on the Navy ROTC scholarship. This was right before Vietnam type time, so they were really, it was during Vietnam time, and they were really trying to get more and more people in, so they gave us some pretty good deals there. Not by today's standards, but by that day's standards they were. But one of the things I had to do was go on midshipman cruises the summers between my years. So between my freshman and sophomore years, that was called my third class midshipman cruise. Between sophomore and junior, my second class, and between junior and senior, my first class midshipman cruise. After my senior year, I was commissioned. So that middle one, the second class midshipman cruise, we were 3 weeks at Corpus Christi, at Little Creek, Virginia, with amphibious Navy and good old Marine training. And then the next 3 weeks we were in Corpus Christi, Texas for naval aviation training. And when we were doing naval aviation training, and actually dumb story, I haven't told y'all this one, have I? The very first plane flight I ever took in my life, okay, was when they flew me from Little Creek, Virginia to Corpus Christi, Texas. I was in a military transport plane. We were in canvas seats facing backwards. Why, I don't know, but we faced backwards. You know, the seats sort of swung a little bit. Not the most comfortable, but it wasn't bad. It wasn't packed in like most airliners are today, but it was definitely okay. But it's the first time I'd ever been in a plane. We were there only a few days before we started our naval aviation training, and my second flight was like 2 or 3 days after we arrived. Second flight ever that I was in a plane. I was in the front seat of a trainer, and an instructor pilot was in the back seat, and I was supposed to be flying the thing. Second time ever in a plane. It was a little single engine, a T-34 trainer, you know, less than a Cessna would be, you know, just a single engine prop. But we, you know, did things for that. The next day, that day he was sort of walking me through things. The next day I was supposed to be doing the landings, the takeoffs, and that kind of stuff. I wasn't very good at it, I promise you. The third day, which was my fourth flight ever, within 1 week now, he took us up to do acrobatics in the plane. Loop-de-loop, barrel rolls, all sorts of things like this. I had my bark bag handy because it was did not feel like that was going to be a good time. I don't think I actually flew up, but I really thought I was awfully close. All in the P1 trainer. The fourth flight I had the very next day, so still within that first week, my fifth flight ever, I was in a 4-engine, I think it was, S2, or maybe a 2-engine S2 or something. Oh boy, that rode like a Cadillac compared to that little single engine thing that bumped all over the place. But then the fifth day, okay, fifth flight, okay, was the jet hop. And they had to take us to another part of the base for that. And that morning, or the previous afternoon or something, they took us through and explained what we would have. When you were in a jet and you were doing these barrel rolls and other things, you had to have on what they call the G suit. Anyone know what that means? It's a gravity suit. In other words, what happens with that is when you're making a sudden change, in fact, it's like you're in a centrifuge swinging around with a very small radius of curvature, then technically all the blood in your body tends to go to your feet. And you can pass out because you get so lightheaded. So what they have these G-suits that have big air bladders that go around your waist, around your thighs, and around your calves. You put those on, strap them in there really good, and then any time that the plane is going through that and it senses that, they inflate, forcing the blood back. And they say when it happens, you had to grunt, you know, and force it, you know, do it a little bit to help it come back, you know. Otherwise, it feels like it's going to cut you in two. I mean, literally, those just suddenly start inflating on you. That would be a lot like a blood pressure sleeve, only much bigger and much faster and stronger. Okay. So, but the whole purpose of that is to keep the iron, especially the hemoglobin, which is the heaviest particles, from going to the extremes of your body, in other words, your feet, and to keep you from passing out. And sometime, if we weren't so short of time, I would tell you a story about what happened then, but we don't have time for that. Okay, I've got the wrong pen here. Well, why can't I find you? Tiara, right? Yeah. All right. Being a pretty good day of attendance, after all. So the most massive particles settle out at the bottom of the test tubes first, just like my hemoglobin tended to do with me, except for those pressure suits, which force the blood back to your brain. Okay. Whoa! And that is the end of, oh, no it isn't, okay? That is the end of the slide set, but if you remember, there was deformation of solids way back here that the slides were out of place because this is the old edition, not the new edition. So I have to go back and find that. Boy, there's a lot in this chapter, aren't there? Ah, here we are. We're getting there. Here we go. Right after pressure, remember we hit these. I said, where are these in the book? Found them way at the end. Okay? Deformation of solids. This, in your book, is 9.10. In the old book, it was 9.3. All objects are deformable. Okay? I think we've talked about this several times when you hit a baseball with a baseball bat. If you hit it hard enough, that ball actually deforms around the bat deforms, but then they spring back, okay? All objects are deformable. It is possible to change the shape or size or both of an object through the application of external forces. When the forces are removed, the object tends to come back to its original shape. If it does come completely back to original shape, an object undergoing this type of deformation that comes back to its original shape is called elastic behavior. And basically, every time you swing at a golf ball, tennis ball, baseball, I told you the story of the volleyball, right? Or did I?
Yeah, we get stuck.
Yeah, okay, somebody was listening, yeah. Those are elastic behavior. Things return to the original shape. However, when a car runs into the side of your car, most of the time that's not elastic behavior. Things get crinkled. They don't pop back to the original shape, okay? So that's, this when they come back to original shape is elastic behavior. What are the elastic properties? Well, you have two things going on. I think of one as the verb and one as the object of the verb. Stress is the force per unit area causing the deformation, okay? When you stress something, you're applying a force to it. It is a type of force per unit area. Strain, though, is the measure of the amount of deformation, so it's the result of the force, okay? It's sort of like hit the ball. Hitting is the stress. The ball is the thing that gets stressed. That acts like the strain. Yes, I'm using the English type for it. So, the first modulus, we're going to talk about several moduli. The first of these is the elastic modulus. It's the constant of proportionality between stress and strain. You apply a little bit of stress, you strain it a little bit. Apply more stress, you have greater strain. The elastic modulus is that constant proportionality between stress and strain as long as it's elastic behavior. For sufficiently small stresses, small amounts of forces, the stress is directly proportional to the strain. So therefore, that is a constant of proportionality. The constant proportionality depends on the material being deformed and the nature of the deformation. Okay? How are you doing that deformation? Okay? So, the elastic modulus is that constant of proportionality. So stress is equal to elastic modulus times strain. Okay? Stress would be force per unit area. Strain would be some sort of measure of deformation. Elastic modulus would be the constant that relates those two. Generally with units. The elastic modulus can be thought of as the stiffness of the material. Okay? Now, think of a diving board. Y'all been on a diving board before? That's usually not a very stiff material. Okay? So you go up and you spring, put weight on the diving board and it starts this motion like that. Okay? That would be a fairly low elastic modulus. But it does come back to the original shape and thing. So the strain is how much you exert the stress per unit area. That's the force that you jumping up and down. The amount that it deforms that board, that's the strain, and the elastic modulus is the constant proportionality between them. Then, as opposed to that, the platform diving, where they just go up on the platform and then they start their motion and then just jump. There is no give there, not much anyway. That would be a very stiff, a very high elastic modulus, the stiffness of the material. A material with a large elastic modulus is very stiff and difficult to perform. Analogous to the spring constant. Remember the spring constant? Coil springs in your car, very large spring constant. A slinky, very small spring constant. Okay. There's another modulus. Okay? This is Young's modulus. And this is elasticity in length. Okay? The other was kind of the bulk. This is length. And basically, this is your diving board, basically, now that I look at it. The bar is stressed. You put weight out here on the end of the bar. Actually, they show you force being employed that way. The length is greater than L0. And this is a linear, so this is elasticity in length, so it's not quite like the diving board. That was counter to it. This is a stretch or a compression. It could be either one. Okay? The external force is balanced by the internal forces trying to hold the bar together. And the tensile stress is the ratio of the external force to the cross-sectional area. There's the cross-sectional area right there. The ratio of the force to the cross-sectional area, that is your tensile stress. The tensile is because the bar is under tension if you're pulling it, compression if you're compressing it. Okay? The bar is stretched by amount delta L, which is usually incredibly small compared to the original length, L0, under action of a force. Now, sort of having a little bit of a issue with coming up with a really good example of this. I can think of several that make sense to me, but they may not make sense to you. Have any of you ever pulled anything with a trailer? A boat trailer or something like that? Well, what you're doing, you're exerting a force on a long piece of metal, and you're tending to stretch it, but it's tending to pull back. That's Young's modulus. Okay, that is that tensile force. Similarly, if you were banging on something, trying to drive something into the ground, like a pile driver or something like that, then you're exerting a compressive force along the length, and the amount by which it returns, that would be Young's modulus. It's a elasticity in length. Okay? The SI unit for stress for that is Pascal. That's the stress. Force per unit area. Pascal. Newton per square meter. That's a Pascal. Now, Pascal is a tiny, tiny amount of stress. Newtons is kind of small, but square meters are huge. The tensile strain is the ratio of the change in length to the original length. Strain is dimensionless. Okay? The stress is in pascals, but the strain has no units. So therefore, the elastic modulus has to have the same units as the stress. So the stress is force per unit area. Here's your Young's modulus. Y is that one. And the change of length per length, that has no units. Now this is meters per meter, okay? Centimeters per centimeter. Millimeters per millimeter, okay? It has no units. So this will have the same unit as your stress does, which is force per unit area. Young's modulus applies to a stress in either tension or compression, either one. Experiments show that the change in length for a fixed external force is proportional to the original length. The force necessary to produce a given strain is proportional to the cross-sectional area. So the bigger the cross-sectional area, the greater the force you can give to give a given strain. The smaller the cross-sectional area, you can create a larger force necessary to produce a given strain is proportional to the cross-sectional area. How big the area is. Okay. Now, here is your classic kind of a graph. The elastic behavior of a material. Usually these are solids. In fact, I think they've got to be solids. Okay? So here is stress in megapascals. Remember I said a pascal is a tiny amount. What's capital M? What prefix does that mean? Mega, and what does that mean? How many?
Megapascal. Oh, you talking like a...
What number?
Oh, 10
To the
six.
Million pascals. Okay, megapascals. Huge. Well, because Pascal's so small, you got to have a lot of them. Okay, your strain, remember, is a dimensionless quantity. 2 millimeters per meter, that would be, okay? 4 millimeters per meter, 6 millimeters per meter, okay? So it is possible to exceed the elastic limit of a material, okay? What elastic limit is, you go past there, you start deforming, and it doesn't pop back. See, you exert a stress here of 100 megapascals, the strain is going to be proportional to it. You release it, it comes right back to its shape. It's elastic behavior as long as this is pretty close to a straight line, because then you have a constant of proportionality, okay? However, there's some limit up there after that elastic limit, then you get bending that doesn't come back, okay? I can remember when I was younger playing with rubber bands, you know, and just liking to stretch and stretch and stretch and stretch rubber bands. But after a while, pop. If I stretch it a little too far, it's not going to come back to that original shape. I have reached well, actually, sometimes it would stretch a little much and not come back. That was when you're in what they call plastic behavior. Elastic behavior was when it came back to the original. Plastic behavior is when it did not come back, and then at some point it would break. Okay? And that would be the breaking point. So when you pass the elastic limit, it's no longer directly proportional. Ordinarily, it does not return to the original length. Now, we're talking about Young's modulus here, but all of it applies. If stress continues, it surpasses the ultimate strength, which is the breaking point. The ultimate strength is the greatest stress that the object can withstand without breaking. And then when you pass that, it shatters. Now, some materials will not have any plastic behaviors. You get up here, and then it's either going to continue or it's going to break. And you can sometimes reach a breaking point right at the end of elastic behavior with no plastic nature. For instance, we're going to try to. The example of this, glass, unless you heat glass, is very brittle. And if you can do a little flexing of glass, a little bit, it'll come back to the original shape, but at some point you do too much and it's going to pop, snap. Okay? So that's probably not the best example because glass isn't technically even a solid, but we'll go. Okay, so what is breaking? The breaking point for a brittle material, like I was just saying, the breaking point is just beyond the ultimate strength. Okay? For a ductile material, what does that mean? Ductile material. You pull on it. Okay. Does taffy mean anything to you?
No, tells it can bend and stuff.
Okay, yeah. When you bend it, but when you pull on it, it actually grows thinner and thinner and thinner. Have you seen people make spaghetti? I mean, actually make it. They keep stretching it out, and saltwater taffy and those kind of things, you just keep stretching it out, and it gets thinner and thinner and thinner. Now, those are lousy examples, but that's what's going on here. That's a ductile material. For instance, copper is very ductile. You can stretch it out into a long, thin wire, okay, or a bigger wire and stuff, but it's ductile. After passing the ultimate strength, the material thins and stretches, never goes back. So that's the plastic material, stretches to a lower stress level before breaking. And that's why the curvature was in there. It's stretching. Okay, there's another type of modulus, and this is a shear modulus. This is elasticity of shape. Forces may be parallel to one of the object's faces. The stress is called a shear stress because it's perpendicular to the direction. This is your diving board. Okay, the ratio of defined as the ratio of the magnitude of the parallel force to the area of the face being sheared. Okay, so you've got one force in this direction, one force in that direction. You're tending to deform it this way, shearing it. Okay, the shear stress strain is the ratio of the horizontal displacement and the height of the object. The shear modulus is S. And the shear stress displaces the top face of the block to the right relative to the bottom, which is either held in place. I guess this one's being held in place, and you're doing it that way. Now, this could also be pulling on a trailer too, where you have this here and something above it, and you could actually be shearing things that way. I can remember operating equipment when I was growing up on the farm. We always had shear pins in things like your mowing machines, your hay balers, and things like this, where the lot was going on, so that if something did, you hit a rock or a stump or something like that, that you didn't see there, then the whole equipment wouldn't break. You would shear off just the pin. You can replace the pin and not have to replace a big, expensive piece of equipment. And those are called shear pins. Okay. Shear stress is force per unit area. Stress is force per unit area. The shear strain is change of X per H. Okay, now what is your X and what is your H? Boy, no good picture here. The delta X is in this direction, whereas the H is in that direction. Okay, pretty much. perpendicular to each other. So alpha of x, F per A, force per unit area, is the shear modulus times the delta x over h. S is the shear modulus. A is a material having a large shear modulus is difficult to bend. Okay? Difficult to bend. Okay. Let me try to illustrate this the way they do there. I don't want to try too hard because this is, I think, a fairly cheap book. But you can sort of see this. Okay? If I push on this, even if I push on it, you see this top moves that way faster than the bottom does. Okay? The more distance there, you tend to get more of that. Now, if this were an old, and you see that I can do some twisting there. That is the shear modulus. We get the twisting type motion in it. Boy, right on the wire, huh? Okay. Courtney's still not here, but Raven is. Get on the right line here. Charity's not. Essence never has come in. Rhea came in, right? Yeah. All right. Good. Attending class today. Only missing Essence, Charity, and Courtney. Courtney's almost always here, so I can't remember. She told me she'd be out this week or not. Okay. So you see you've got the shear action going on here. One force is in that direction, the frictional force is this way, so you get that kind of relation there. Material having a large shear modulus is difficult to bend. Let me get my book open again. Hope I'll put this back in the right place. Yeah. Okay. There is no volume change for this type of deformation. You're not changing the volume any, just changing the shape, so to speak. Remember, the force is parallel to the cross-sectional area. So the force is in the same direction of the cross-sectional area. In tensile stress, the force is perpendicular to the cross-sectional area. It's parallel in the shear stress. Then we have bulk modulus, and this is volume elasticity. This would be more like hitting the balls, like the baseball or volleyballs or whatever. The bulk modulus characterizes the response of an object to uniform squeezing. Okay, suppose the forces are perpendicular to and act on all the surfaces, so when the object is immersed in a liquid, then it tends to be force acting from every direction, and that is a bulk modulus. The object undergoes a change of volume without a change of shape. That's a bulk modulus, volume elasticity. Usually when you release it, it comes back. So in this case, if you put something under pressure and the whole thing reduced in size, that's what we're talking about here. Volume stress, delta P, is the ratio. Why in the world they use P, I'm not sure. Oh, wait. Volume stress is force per unit area, which is pressure. Okay, so that's why they use P. Is the ratio of the change in the magnitude of the applied force to the surface area. So if you're doing the surface area of the block, you add up the surfaces of all 6 sides. If it's a sphere, the surface area of that sphere. Okay? This is also a change in pressure. That's why we use delta P. The volume strain is equal to the ratio of the change in volume to the original volume. And again, there's no units on that ratio. So in other words, your bulk modulus coefficient is going to have the same units as pressure, And the uniform bulk shrinks, the cube shrinks in size without changing its shape. And here is that bulk modulus. delta P, change of pressure, okay, force per unit area, is equal to minus B times delta V over V, change of volume over volume. Well, here your delta P, change of pressure, inlet, in, so a greater pressure here is going to make a smaller volume, so therefore you need the minus sign. When the pressure is going up, the volume is getting smaller, okay? Material with a large bulk modulus is difficult to compress. The negative sign is included since an increase in pressure will produce a decrease in volume. The B is always positive, and that's called the compressibility, is reciprocal of the bulk modulus. Bulk modulus is capital B, compressibility is reciprocal, 1 over B. So the notes on the moduli: solids have Young's modulus, which is this way. Bulk modulus, Young's modulus is this way, tensional or compressional. Bulk modulus is volume, and shear modulus is the twisting type thing. Liquids have only bulk modulus. You put a pressure on a liquid, it's going to compress or expand evenly. You can't have shear or tensional. There just aren't any. They will not undergo shearing or tensile stresses. A liquid would flow instead. But a liquid will compress, and that would be bulk modulus. Ultimate strength of materials is the maximum force per unit area that material can withstand before it breaks or fractures. That's supposed to be a fractures, not factors. Okay, that should have an R in it. Okay. Some materials are stronger in compression than in tension. Okay, so they may be able to compress them more, but tensional, they'll fracture more easily. So let's look at a few applications of these. I'm not keeping up with the book very well here. This is over on page 309. Now there were some pretty good examples there, and I really want to emphasize some of these. Built to last, compression type thing. Football injuries, compression type things. Lead ballast overboard. And now we're going into arches and ultimate strength of materials. Horizontal beam supported by 2 columns. That was used in the Greek temples, for instance. The columns are closely spaced and the strong material across the top. Limited length available in stone, so you usually had that horizontal beam, especially if it was stone, you were limited to what you could eat, so you had to have your columns there and your the big long piece to go across the top. Nowadays we use all sorts of things. In wood construction, you call it a lintel, where you have a pretty strong piece of material over a doorway, and that's what you use there. Here that was stone. The low ultimate tensile strength of sagging stone beams, you don't really want that to happen, do you? Okay. So a lot of times they will use then, even in stone structures, they will use a steel beam across there. And in home structures, they will sometimes do that too. If you have a wide expanse. When we built the bungalow over on the farm in Georgia, my wife wanted to take out a wall and have a open up the room some, have a great area, so to speak. Well, they already had a pretty good wide area from the end of that original room to the kitchen. That was a wide area. And then she wanted it extended on down here. I said, I think we're probably going to need a support post there. They ran it by the engineers and they said, yeah, one here should work. And they brought in a really heavy duty, it was made out of wood product, but put it on edge, several planks together of it, and that provided the strength. if you have it on edge like this, rather than this is going to tend to sag, this will not tend to sag as much. So they did that. So this, it was a posted beam type structure there. It just didn't have a wall on either side. And then they finished the post really poorly. Okay, we got them to fix that some. Okay, now later they said, hey, wait a minute. The Romans said, you're limited by how long a piece of stone you can put there, find there, and how strong it is. And they found out if you used a semicircular arch, you could have really small stones and still hold the same weight. Anyone know what this one at the top is called? The keystone, exactly, the keystone. And that's the one. All these others, see, all the weights on here. Now, when you get up here, though, you see the force is distributed somewhat here, but that one is the one that ties them all together. If you've ever gone to the McWane Science Center, they have a real fun little thing. They're all cushy things, and you can build your arch there, and it will stand by itself and actually hold quite a bit, you know. And it's surprising how much you can do with that. Allows for a wide roof span on narrow supporting columns. The stability depends on the compression of the wedge-shaped stones. That's the compression here. And that was the semicircular arch that the Romans brought in. The Greeks just had the flat. The Romans improved on that. One of the few things the Romans did better than the Greeks, I think. And then they came out with the Gothic arch, used in Europe in the 12th century. Those are extremely high and supported by what they call the flying buttresses. Okay, it kind of distributes the weight to the various things there. The Gothic arch coming up very steep here. That means that there's, because the angle is smaller, you distribute the weight over more of the structure, and then you have more distributing on out this way. Flying buttresses are needed to prevent the spreading of the arch supported by the tall, narrow columns. So that was your Gothic arch. Variation in pressure with depth. Did we already do this? Yeah, I think we picked up and went on. Yeah, we covered the rest of it. Now, just a few examples. Have you ever noticed the big flatbed trucks? Big, long flatbed trucks that will pass you on the highway sometime. And if they're empty, look at them. You'll see sort of an arch tilt. When they get a load, though, the load pushes that down, but it usually doesn't push down past this. That way you're using some of that tensile stress and other kinds of stress to support your load. And it really is pretty neat how that works. That does finish the chapter, okay? Yeah. I'll get to that later. Okay, at the end of the chapter there is a summary there. Goes over each section, states of matter, density, some of the big terms are bold-faced, a couple of the formulas are given. Variation in pressure with depth, that's given, formula there, and Pascal's principle. Buoyant forces and Archimedes' principle, those terms are defined, plus the formula for buoyant force. Fluids in motion, equation of continuity, Bernoulli's equation, and combinations of those. Deformation of solids, and that's what we were just talking about, the stress, the strain, the various moduli, elastic modulus, Young's modulus, and bulk modulus. Okay. Then there are conceptual questions, well worth a look. Lots of pictures there, you can read and study those, and then the problems, these are closer to what your test questions would be. 9.1 didn't really have any, but 9.2, any of the odds 1 through 7 will have their answers in the back. From 9.3 and 4, 9 through 15, those have answers in the back. Then 9.5, 17 through 31, quite a few of those answered them back. 9.6 and 9.7 are together, and that would be 33 through, odds 33 through 47, quite a few of those. And then they have surface tension, capillary action, and viscous flow, what we started talking about today, 49 through 59. Transport phenomena, 61 and 63. Deformation of solids, 9.10, that's 65 through 75. And then you have additional problems which tie several of those together, 77 through 91. All right, and for those who came in later, let me go through just a couple of things. Please get your papers in, folks. I've received fewer, well, right now half of the papers have come in, and we only have two class days left after today. Okay, so get them in today, tomorrow, Wednesday, or Thursday, or Monday's the last day I can accept them without you losing points. I will take them later, but you'll be losing points after Monday. You'll still get a bonus point if you get them in this week. No bonus points on Monday. Start losing points beginning on Tuesday. I don't have the test ready for this chapter. I'll go back and check. I went through last week and could not find it, so I've got to work it up, and I was working on our planning hearing, which is coming up tomorrow, and I just didn't have time to get it done. But the lab today I didn't have time to do either. I tried to find it, I couldn't either. So we're going down and do the lab right now. What you'll need is paper. Lined paper, unlined paper, I don't care. You'll need a piece of paper to do your lab on. I don't have the thing typed out for you, but it's going to be pretty simple, pretty straightforward, not going to take a lot of time. So what I'll do now, if you want to take a quick break, you can. I'm going to let me go check. I think 259 is open. If somebody wants to go down there and check, come back and tell us if the people's still in there. But I think it's usually open by now. And by the way, I'm not going to have a chance to, for those who came in late, I won't have a chance to do any grading until tomorrow afternoon. And even then, I've already got a bunch of people stacked up. They're going to come see me tomorrow, so I won't get a chance to do much. But tomorrow morning's office hours, I'm over at a planning hearing on the Birmingham campus. We have class today and lab today, then we have class Wednesday, and then the last class will be the following Monday. I'll give you your last test then. I'll give you the test for this chapter, hopefully, on Wednesday. Yes.
So our last class next Monday?
Yes, and then I'll give you your final exam and bring it back either Tuesday, Wednesday, Thursday. I've got to have it by noon on Thursday because I've got a treatment on Friday. Even though school will be open, I won't be here.
So we bring it back like 5 last time.
Oh, that'll be fine. I'll either be here or in my office. More than likely in my office. Okay, and we'll start next time on chapter 10. Okay, head on down. I'll be there in a minute. I've got to disconnect my projector here. Let's see, I can just end this. Yes, sir.
I need test.
Okay, let's go on down to the lab and I'll get it to you there either before or after.
And the labs go.
Okay, I'll get that. Head on down, 259. If you find out somebody's in there, come back up here, we'll find another lab. I've got to get this disconnected. Okay, so you each have a box, you each have a ruler, pairs of two, okay? Okay, so what I would recommend is that you, and any way you want to do this, you set it up like you want to. Okay. Say aluminum, iron, brass, and copper. Okay? Now, you got a cube there. Okay? So with your ruler, and use the centimeter scale, measures the length of that cube, the height of the cube, and the width of the cube. Make sure you get all three separate, because they may not be exactly the same. If they're really cubes, they will be, but get it to the nearest tenth of a centimeter. In other words, to the nearest millimeter. So do that for aluminum. So it'll be length, width, height. You'll have a blank for each one of them. Then you have another blank for volume. Okay, this is your calculated volume. How do you get that? Exactly, multiply them. Now, each of these have units. I just said do it to the nearest tenth of a centimeter. So you have so many point something centimeters. So when you multiply them together, you'll get cubic centimeters. Okay? And while y'all are doing that as a team, write that down, and then I'm going to bring up scales. Okay, in fact, some of you can do the scales first if you want to. Okay, I'll put one scale here and one scale over here. So I would say actually do this before you do your lengths and width, but you only have two scales, so use your time wisely. So you also have mass. Okay? Okay? And then you'll have your calculated column, which is density. Okay? Oh, and by the way, be sure you zero the scale before you do your measurement. Right? Zero the scale before you do your measurement. And if you did, that's up to you. You're the one going to be measuring. Now, each of those little bitty black tick marks there is 1 gram. So you're measuring from the scale. Everybody listening? You're measuring your mass in grams. Okay? Measure that. Measure your length, width, and height. Calculate your volume, and then density. What would density be? What formula for density? Hint. You just measured your mass. You just calculated your volume. What's your density? Mass per unit volume. Exactly. Now we're going to do something else. Okay, that's going to be 1, 2, 3, 4, 5, 6 times 4 is 24. Okay.
Now we weigh all these, right? So we weigh all these, right? So we weigh all these, right?
Yeah. Determine the mass. I'm sorry? Yeah. Okay. Okay, then calculate this. Okay, wait, let me, I didn't think about it. I forgot I wasn't connected to it. Was there a question? Yeah. Okay. In whichever order you want to. I wish I'd have said. Still see? Okay. Goodness gracious. Oh, I want this work study suited really badly. These boards are in miserable shape. Okay. This is basically, okay, everybody watching? Now, I can't do anything about this. This is just smearing on the board. But here you have your column. If I were going to rearrange it, I would do aluminum, iron, bronze, and, brass and copper, okay? I think I would do the mass first, but you don't have to. Mass, length, width, volume, height, volume, and density, okay? Now we'll have one more column here that everybody will do together, and that will be think of a good thing to call it. I'm going to call it capacity, but it's actually the same as volume, okay? So, okay, and then we'll do we'll get to that. But when everybody has finished doing your mass, only two scales here, and Ryan ripped one of them off, okay? One up there, someone left a block on it. Need all the blocks back in the boxes, okay? Your mass, length, width, height, volume, density, and then later we'll do capacity. Okay? Who left the block on the scale? Somebody's missing a block. Looks like a brass block. No, a copper block. Who's missing a copper block? Huh? Block head. No, I'm just kidding. Okay. Okay. So everybody sees what the blanks are. Okay. And all the teams, their scales are available. Okay. Determine your masses. Determine your lengths, width, height, volume, Are there any questions? I'm going to put this on pause if there's no questions right now. How are... Say this again. Okay. Someone help us out. How do we calculate density? Mass per unit volume. Mass divided by volume. Any other questions? Okay. Okay, we're actually going to do the volume in two ways. The way you're to do it right now is multiply the length times the width times the height. Okay? Now these are all in what units? Centimeters. That will be the nearest tenth of a centimeter. And your volume will be in what unit? Centimeter times centimeter times centimeter is cubic centimeter. Like 2 centimeter by centimeter would be square centimeter, by another one would be cubic centimeter. And we will do it one other way, and we'll see how the two compare. What's that? After you found what? Okay, you got it for all 4 blocks? Okay. Then, and what I'll do is turn this off for a moment. Because I need to take my computer over there. Okay. Has everybody finished taking masses? No? Okay, there's 2 scales. Please take advantage of them. But let's pause for now before you get your masses. Okay? And let's do another way to determine volume. Okay? Now your cubes were nice and regular and even and stuff, right? However, what if we had something that was shaped like this, and we needed to determine the volume? Impossible?
No.
How?
We use water.
Okay, we're going to displace water. We're not going to use this, that's not mine. But we will use your cubes so we can see how good the 2 different methods are. So I want someone to come up here and pour water from here into there until you fill it.
Until I fill the whole thing.
Until you fill the whole thing.
Someone stop.
You determine that.
All the way to the top.
All the way to the top. Are you at the top?
Pretty close.
Ah, he exceeded. Okay, good. All right. Now, what did you notice there? Looked like he was filled, but he could still add more. What do you notice now? Any of you see? What would you say about the top? Huh? Yes. The water is actually higher than the top of the container. Why is that? Second? Surface tension, exactly. Exactly. The surface edge of the water is hanging on to those molecules like crazy. Okay, so I'm going to bring his aluminum up here. That's one, yeah, anyone will do it. Okay, now what I want you to do is very slowly and carefully lower that into the water, but don't let your fingers touch the water. So before your fingers touch, drop it. Okay? Wait till all that settles out, and then pour that water into that dry container. Okay, put that back under. Okay? Pour that into there. Now, this is measuring how much water was displaced. And this is in milliliters. What did you calculate volume in? Cubic centimeters, exactly. What's the difference between milliliters and cubic centimeters? Precisely the same. So you could just read this and write it as milliliters or cubic centimeters. Read the volume you have there. Now, it's past the bottom. Okay. If you'll hold this just for a minute, right there. Don't let it go forward and spill. Okay. Pour that into here. We won't need that one. Oh, yeah. Slowly, carefully. Look at you.
Sorry.
All right. I think we're going to have to fire them. Okay.
Wasn't much.
I know. Okay. Don't need that anymore. Refill that. Yeah, that's all right. Refill it. Okay, sorry. Okay. Put up the second over there. Someone else's aluminum block. We might need something else. Okay. All right. You got the idea? Okay. Just some pour into that and get all the water out of here. Put that into there.
Oh, okay.
Pour that into this. Slowly and carefully. All right. How much water's in there? Again, this is a milliliter. I'd say leave it on a flat surface and you spot that and go. Otherwise you're going to tilt. See it?
It's like
18 what?
milliliters.
18 milliliters. So that's what you put by, okay, it's not on the board anymore, by capacity of the water. 18 milliliters. What did you get as your volume for aluminum? Second? 15. Okay? So that was 18 milliliters. Okay? You can now drop iron in. Now, someone else want to drop? I don't want to work this poor guy too hard. Okay. Again, try not to. Oh, yeah, okay. All right, iron capacity. All right. that lot bigger? What did y'all get on the value of iron? Are they all about the same?
Yeah.
13. How did this? Did you dump the
I dumped the water out,
water?
yeah.
Huh?
Dump the water out.
Okay, it must have done some splashing or something. Okay, but what did you say? 30? What did you
That's
say?
32 and a half, I think.
32 and a half is the capacity of water for the iron. Interesting.
Dumped it out.
Okay. All right. See, that much more was actually splashed before, because it should be right at the top. All right, which is next? Bronze?
Brass.
Brass, I mean. Okay.
It's hard not to, like my fingers.
Capacity of brass?
What was that? 26 and a half.
26 and a half. What can we get?
Yeah.
Again? 23 and a half for copper.
What'd you say?
Okay? Which of those seem to be the least, the farthest off? Aluminum and the iron, maybe. Yeah.
Which one? What did we just say this one?
That was copper, and it was 23 and a half.
23 and a half. Huh? I don't know. Y'all are writing. Who wrote down aluminum?
18.
What's that?
18.
18. Huh?
Should I grab these now?
No, let's get another aluminum and try it. Okay. Right up in here. So we can slide it over now.
The 21.
21 for aluminum. You can change that if you want to or whatever. Okay, let's do the iron again.
Alright.
Is that all we got?
21? Okay. I think we got our technique down a little better toward the end. We're all pretty consistent there. Okay, let's see if okay. Everybody get that last recording? Yeah, I was just going to see it home. You can run that with the forward with the skill, so you can pick it up to the second. Yeah, put some of it in there. Yeah, well, that's all right. Oh, let me see if I can find papers out. Okay. Okay, just put them on the counter. I'll pick them up later. Okay. Now, I want you to redo the density with the capacity measurement. Mass per unit volume there. Okay? So you have another column of density. I didn't leave enough room on my sheet for it, but you can. So you have one density that's based on volume and the other based on capacity. And see what you get. They shouldn't be far off, but see what you get. Oh, you haven't done your weights yet? Okay, do your weights. Y'all haven't done your, okay. I'm sorry?
What did you say about the plot in the second density?
That was a
Do what?
Capacity times. What did you say with the capacity times what?
No, okay, you do, your new density is your mass divided by the capacity. Yeah. Capacity was also, you could either put milliliters or cubic centimeters, same difference. I'll get this out of your way. Okay. All right. So you actually wind up with two densities. One was based on volume and one based on capacity. Okay? Now, I'll let everybody get caught up. Okay, I'm going to put this back on pause for a minute. Okay, I think there were a couple questions. What was that?
Is this density grams per milliliter?
Okay, you can either write it as grams per cubic centimeters or grams per milliliter. They should be exactly the same. Okay? Oh wait, I mean a cubic centimeter is exactly the same as a milliliter. Your answer is probably not going to be the same, but see what they are. Okay? So you'll have a row for each of these: aluminum, iron, and by the way, use the larger of the two aluminums and the smaller of the two irons. Remember, we had an iron that was in the 30s capacity. Don't use that one. We had aluminum that was like 16 or 18. Don't use that. Use the ones that are close together, like 20, 21, whatever they were. Okay? Now, has everyone calculated two densities so far? One based on volume, one based on capacity. And for each of the metals. Okay? Yay or nay? Yay. Yay! All right, never mind. All right. Now, what were the four metals we had? Aluminum, copper, and iron. Aluminum, iron, and copper. We did not have brass in this column. So we are going to compare what our densities were with the ones in the book. So you're going to have yet another set of densities, and this is the standard density. So your next density is going to be rho S, okay? Or you could call it A for actual, whatever you want to call it. But we only have these three, so put this down too.
This is our last one for the
Okay? So everybody got this? Aluminum, 2.70 grams per cubic centimeters. Iron, 7.86 grams per cubic centimeter. And copper. We don't have brass. Okay, I don't have that for brass. Because brass can be a variety of things. It's an alloy, and it could be different mixes. But copper is 8.92 grams per cubic centimeter. Okay? Now, two more columns. Okay? One is percent error by volume and percent error by capacity. Okay? And here's what your percent error is. First, let me tell you what your error is. You can do a column for this if you want to, but it's up to you. Error is measured minus actual. Measured minus actual. So your measured for the volume one would be here, here, and there. Okay? Your actual for aluminum is here, iron is here, and copper is there. So that's your actual error. And then to get the percent error, divide that by actual, which is this number again. And then multiply it by hundreds. So this is percent error. And you'll do that for aluminum by volume, iron by volume, and copper by volume. And then also do it for aluminum by capacity, iron by capacity, and copper by capacity. Because you have different measured density. You have the density by volume here. That's what you put here, minus this one, divided by this one, times 100. That would be your percent error for aluminum by volume. Then you do the same thing for iron and copper. And then when you do your density by capacity, do the same thing. Your measured, that would be this one, minus actual, that would be this one, divided by actual, and multiply by 100. How have you done? Yes. Which?
I guess the error, the first error is
Okay, your percent error Your actual error is your measured minus the actual. So this would be your measured here by volume minus your actual here divided by the actual, and then multiply by 100 and make it a percent. Then you'll do the same thing for capacity. This measured minus your actual divided by actual and multiply it by 100. Okay? Okay. So, what I'm going, yes? A little louder. Okay. Let me redo my columns here completely. Okay? And you can keep them however you want to, but be sure you have these things down. Okay. We got aluminum, iron, or brass was next, wasn't it? What was after aluminum, brass or iron? Which was after aluminum, brass or iron? Say again? Brass, okay. Yuck. Okay. Okay, aluminum, brass, iron, and copper. Right? Is that the order? Copper, brass, copper, iron?
Flip BR and F.
BR, okay, yeah. It was iron and then brass, wasn't it?
Yes.
Okay. I thought I had it right, but okay. It really doesn't matter, but just since you took it that way. Okay. Iron and then brass, right? Okay. Here, in whichever order you do it, you had mass, you had length, you had width, you had height, you had volume. I'm going to put volume calculated, okay? You multiply those together, okay? Then you had density, and this is density by volume, right? Then you had capacity, which is what we did with the water, right? And then you did density by capacity, mass per unit volume in this one. Okay? And then you had the actual density. Okay? And I'll write down the actual densities. Aluminum, 2.70 grams per cubic centimeter. Iron, 7.86 grams per cubic centimeter. And copper, 8.92 times 10. Oops, not times 10. Grams per cubic centimeter. Okay. Then you had percent error by volume. And then you had percent error, I can't write, percent error by capacity. Okay? Now these you'll only have 3 for that because we didn't have brass, but everything else you'll have 4. Let me put this volume I'm just going to leave that volume, not VC, because I'm afraid you're going to confuse the C there with capacity. Okay. Okay. Is that making a little more sense? Okay. And you can have them in columns wherever you want to. But those are the data you need. This is percent error by. Now, some of you have done some of the calculations already. Which came out better, your volume or your capacity? Volume did? Okay. I thought there was a little bit of error in the capacity.
Could you say one more time what, how to get those two?
Oh, you get what?
How you get the percents?
Okay. Okay, percent error. I'll put it down here. It's your measured, and your measure will either be, that will be one measured, and that will be a measured. Okay? Minus actual, these are your actual right here. Actual densities. Divided by actual, that same number there, and then multiply it by 100. Okay? For this column here, you use the volume, density by volume. For this one, you use the density by capacity. That's probably not very helpful. Let me pick me a color. Green. Okay. This one will be by capacity, and the black one is by volume. Let me. Okay. See, the measure down here will be for this column, these measures, and for this column you use this measure. I'm sorry this board is in such terrible shape. How we doing? Any questions? I want to be sure you got. Yes.
I got a negative.
You got what?
A negative.
You got what?
A negative.
You got a negative. Oh yeah, yeah. Well, that meant okay. Your percent error was negative. Yeah, that meant your measured was less than the actual. So you were off by. Oh yeah, yeah. That's fine. But it's still not a huge number, is it? What were some of your percent errors that you got? Just give me a few.
I got 0.2.
Okay, when you multiply by 100, or before or afterwards?
After 100.
Wow.
On the measurement, we got 8.9, and then 8.92 is the density. So.
Okay. Oh, you mean for what? Copper?
Yeah.
You got 8.92 on the nose?
Oh, yeah.
On one of these?
8.9.
Huh? 8.9.
Yeah, 8.9.
Okay. So yeah, that's a very good. And which was that? By volume or by capacity?
That was volume.
By volume. Okay. Okay. Does everybody have a good enough understanding of what you need to do? You don't have to finish it today. You can take home and finish it if you need to. Huh? Is this the last lab we're doing?
No, this is the last column.
Oh, yeah, yeah. I mean, that's it. When you get all this stuff, you're done. Sure.
Okay, so for the formula, n minus a over a times 100.
Right.
So I would take this 15.6.
Okay, now your rows. Row by volume, 2.9, 2.9 minus 2.7
divided by 2.7.
divided by 2.7, and then multiply. Yeah. Okay. When you're doing your errors, what's measured here is your measured volume. Not measured anything else. Measured measured density. Measured density by volume, measured density by capacity. Your actual is your actual density. Okay? So make sure you're only subtracting and dealing with things that, by the way, be sure you put your names on your labs if you're turning in today. Okay, what you need. Is it all right if I turn off the projector? Does anyone need it anymore? Let me see. Okay. What do you need?
This test I turned in, I think 6, 5, and 6. I turned in 5 and 6.
Right.
Lab for 5 and 6.
You don't have the lab for 5 or 6. Okay. That's what you deal with the friction lab.
And so, like 3 pages.
Yeah, something like that. Thank you. Okay, did you work in power when you went did the stairs? Okay, there's that lab. Might be a get with somebody and turn it in that. When you did test body, you turn that into that. Okay, you did do the lab on momentum. Okay, this one. First page is you answer questions from the book, and the second page is probably a little bit data, or you can listen to the YouTube video. I think it's on there. Okay? You got test 7 already? No, I have. Wait a minute! I do have test 7! I forgot I had a copy. So here, anyone who needs a test 7, come and get it. This is today's chapter. I forgot I had this one copy. Okay, sure. Okay? Yeah. Do you have questions? Okay. Oh, you're good. Okay.
You said density by volume.
Say again?
You said density by volume.
Right. Okay, that. Yeah. Glad to get rid of these papers. Okay. So you calculate the density by volume. You got that already? Mass divided by the volume, right? Okay. And then this density by capacity is mass divided by the capacity. Okay? So they should be fairly close. I mean, not super close, but fairly close.
Basically, we asked what's the formula for these.
Okay, well that's what this is. Okay, but you have these two. Okay, and those are fairly close. Density by volume and density by capacity, right? Okay, those are your measures. So in your percent error volume, you do the density by volume minus the actual density equal, divide that by the actual density, and then multiply by 100. And density by capacity would be error by capacity would be density by capacity minus density by actual divided by density. Okay.
Can I say that too?
Okay, wait.
What test y'all did last week?
What's that?
What test did y'all do last week?
If you turn in 5 and 6, this is 7.
Oh, that's it?
Yeah.
My bad, I didn't even say that out loud.
Okay. Okay, the formula is, for percent error volume, is the density by volume minus density actual divided by density actual times 100. Right. That's it. By capacity is density by capacity minus actual density divided by x, and then times that.
I made everything real clear. I know that out.
Okay, are there any other parting questions? I got another class starting in just a minute. Any other questions?
I got you.
Did you get your test? Okay.
Yeah, I got you.
Okay, yeah. Okay.
Can I get the test 22 from chapter 22 and lab from chapter 22 for
Okay.
202?
You mean in that the next class?
Yeah,
Okay.
that was from last Wednesday.
Right. Well, can we do it when we get into the next class?
Yeah.
Okay. Because I'm all into this one. What's that? All right. Glad to. Did that answer your question?
Yeah.
Okay. Does anyone else need test 7?
Me, I think. Okay.
Anyone else need test 7?
Me.
Okay. Was that the same me or is that a different?
Same.
Okay. Thank you. Anyone else need test 7? Oh wait, there's one right there. Who's that? Huh? Who's that? Whose is this? Okay. Have you got 1 or 2? 1. You need 1 too?
Yeah. The test is not mine.
Oh, the test.
The phone is mine.
Oh, okay. So I thought that was her test. Okay. All right. Oh, if you had turned in test 6? I think so, but let me check.
Oh, would it be in the grade book?
Say again?
It wouldn't be in the grade book.
I don't know. Okay, you mean you think you turned it in early? That's 6. No. Yeah, it's already in.
And we're not having lab for, no, you said that Wednesday. Last week we're not having lab for the 202 that starts now.
I don't think we'll get far enough.
Yeah.
For that. Well, we might. I don't know. All right. Thank you.
Also, can I see that? Can I see that? I gotta change the title on one.
What did you say?
What I just put in.
The lab today?
Yeah, I put PS instead of PA.
You did what?
I put PS for the standard instead of PA.
So you can
Bradford, Opium, Eames, Noble, Ball. I'll be back up in the classroom. I've got to go up and meet with my next class. Oh, I gotta put away these things.
I need the 6.
I'm sorry.
I need 6.
That's 7 today. Anyone else need test 7? Okay. Now, the other thing, did everyone put his or her blocks back in the box?
Where are you gonna be after this?
Back in the classroom. I'm sorry? I'm sorry? Yeah. Did you get that? I'm sorry?